So thanks a lot for the introduction. My name is Alejandro, and I'm both at UQ and the Jameson Trauma Institute. Today, I'm going to be talking about assessing movement after neuromuscular impairments and talking a little bit about the opportunities and challenges of using wearables for these purposes and how open source can actually help us achieve this purpose. I want to start a little bit by talking about stroke. So 1 in 4 people over the age of 25 will have a stroke in their lifetime. So think about it. 1 out of 4 people that they're in the room will probably experience a stroke. Now, what's happening is we have, in 2019, 30.7 million new strokes each year. And with advances in technology and medicine, we're actually getting better and not letting people die from a stroke. But what's happening is this is creating also a strain in the healthcare system, because approximately 65% of stroke survivors have a long-term disability, which impedes their ability to carry out daily activities unassisted. So we need to do something about how we can deliver rehabilitation interventions to be able to bring these people back to the community. Now, there's a problem. When you talk about neurorehabilitation, no approach seems to be superior. So what I'm showing you here is a clinical scale. It's called the Fugl-Meyer. This is specifically targeted for the upper extremity. So think about the typical assessments that you do in the clinic, where you lift your arm and so on. So it's a little bit of rough scale. So higher value represents better improvement. And on the x-axis, I'm showing the number of participants across different clinical trials. So the bigger the bubble and the more to the right, the greater that clinical trial it was. The different colors represent the different technologies used for those clinical experiments. So it could be a robotic-assisted intervention, constraint-induced movement therapy, mirror therapy, electrical stimulation. What I want you to notice here is the more you increase the subject, the more you tend to regress to the mean, right? So it really doesn't matter what you do. You're probably going to achieve an improvement around 4 points in the Fugl-Meyer scale. So when we're talking about clinical significance in intervention, what we want to achieve is something above 6 points in the Fugl-Meyer. So my research is about that. It's really about trying to understand better ways to recover after stroke with the use of technology. And what we know from the previous research is that, yes, we're not doing enough in the clinical practice. We need to be able to intervene as early as possible. We need to increase practice a lot, 30 plus hours per week is the recommended. The studies that have shown most successful in current practice. If you think about it, the number of hours that a patient receives nowadays is approximately 1 hour per session, 3 sessions per week. So it's almost nothing, right? We need to be able to adapt the training with the right challenge and the right motivation. So essentially enable personalization of the training interventions. The other thing that we know is that the current outcome measures, the clinical scales, are not good enough to help the field move forward. So we don't know how to stratify patients in order to investigate novel drug interventions, for example. We still don't know if the achievements if the improvements that we see in patients is because of true neurological recovery, neuroplasticity, or as a result of compensatory strategies. So think about when you're trying to move your arm after a neurological injury, is it because you're actually able to move your arm, or because you're engaging into trunk movements or some sort of weird body motion? And we still don't know how to predict or target the right interventions. So there's a huge opportunity for assessments in this area. So my group focuses on that. So I was working in Switzerland back in the days. I moved here just before COVID in 2020. And my group focuses on how to effectively promote neuroplasticity and try to maximize that functional recovery. We do that in 3 pillars. So trying to understand how we move via movement analysis, using neuromechanical models, or motor control, motor learning experiments. And then we use that knowledge to create or develop rehabilitation and assistive technology. We don't try to develop technology from scratch, but rather maybe modifying the existing solutions in order to make it work with the underlying principles that we find in the first pillar. And of course, we're very interested in understanding what works and what doesn't work. And for this, we need to develop valid, reliable, and sensitive measures of movement performance. And the more we're able to measure that, the more we understand, and the more we can restore, and the cycle completes. So we use an integrative approach of engineering and clinical sciences for that purpose. To give you an example of the work that we do, we tend to work very closely with basic scientists, industry, end users, and clinical research to develop tools like exoskeletons, for example, or using artificial intelligence to make sure that we develop tools that are simple enough to be used in the clinical practice, but not necessarily simplistic. What you can see here is an exoskeleton that we're trying to simplify as much as possible to be able to use overground in small clinics around Australia. But we're also trying to incorporate advanced neuromuscular models to be able to control the exoskeleton in a way that maximizes activation of certain muscle groups, for example. We're doing research on wearable sensors, so we're trying to make sure that the measures that we develop are consistent with the clinical population in question. We're also making sure that we develop technology, and I'm gonna be talking a little bit more about this, that can be scalable and that we can produce and collaborate to generate better relevant results in this area. We work on computer vision technology to make sure that the technology that we develop is unintrusive. So sometimes you don't want to attach anything on the participants in order to assess the motor function. And we can also use these algorithms to enable more robotic devices to be safe with the physical interaction that these devices have with the patients. Finally, we also work on virtual reality, and we're trying to see how we can engage practice, how we can create motivating environments, and how we can explore different ways in which we can provide feedback to be able to measure different parameters of interest. For example, range of motion, the use of compensatory strategies, or synergistic movements that we don't want to observe in patients. So today I'm going to be talking mostly about wearable sensors and essentially how we can work towards valid, reliable, sensitive measures for evaluating movement after neurological injury. So of course, I think we're all here trying to work with wearables and e-health platforms, and they're extremely promising, but we need to tackle a few issues. First, the validity of outcome measures from wearable sensors on impaired populations is questionable. What I'm showing you here is the comparison between a Garmin wearable and an active PAL, which is another wearable that you use, and the step counts that these devices measure for different levels of severity. So what you notice here is on the right, the comparison between those two sensors, they are very similar, which means that they are mostly measuring the same thing. However, for participants that only walked a little bit, there's a huge variability, right? So what this is telling us, and there's some other more evidence, is that the measures that we're getting from the sensors are not applicable for someone that has a severe motor impairment. So for example, if you're walking with short steps, if you're walking with a walker, with a crutch, they simply don't work. So we need to develop population-specific outcome measures that are device agnostic. There's another challenge, right? So our ability to interpret uncontextualized low recordings is very limited. Current wearables are very good at monitoring general activity, the amount of activity counts, acceleration counts. We're becoming better at quantifying types of activity, for example, walking, arm use, sitting, standing. Again, there's a problem that these algorithms do not translate well into clinical populations. We can use these measurements to, for example, measure the relative use of a limb if you're wearing two of them. But when it comes to movement quality, for example, the smoothness of the movement, the coordination, how is this improving after you have that neurological injury, and to make sure that we are measuring the progress of patients correctly, we're really much behind, and these sensors cannot measure that. And the reality of movement quality measures using technology is really bad at the moment. So think about it from the engineering point of view, right? So if someone asks you to measure the size of a room, it doesn't matter what technology you use, if you use a measuring tape, or if you use a laser measurement system. If you're measuring distance, you're expecting the measures to be the same. When we're talking about measures for movement and for rehabilitation, you can use several technologies. For example, you can use technologies that measure hand position. You can use technologies that measure your angles. You can use wearable sensors that measure angular velocities and linear accelerations. And if you apply more or less the same construct, the same movement quality measure, you don't get the same. So essentially, we should be worried about it, right? Because we don't understand what exactly it is that we're measuring when we're using these technologies in clinical practice. The other problem is we tend to use very subjective terms in the field. For example, when we want to measure smoothness, there are different ways of measuring smoothness. So I can have an evaluation of a session from a patient. So here is the hand trajectory performed over 30 sessions. So you can see the hand trajectory of a participant on 8 different trajectories. And you can see that the trajectories become more or less smoother, right? So if I use the first measure, I may conclude that the patient, in fact, got worse, right? Because I can see a decline in that measurement. If I use the second measurement, which is also called YERG, I may conclude that there was no change in the performance of this patient. And if I use the third measurement, then I can conclude that that there is, in fact, an improvement of that. So we should be worried, right? Because we can have self-fulfilling prophecies to prove or disprove whatever hypothesis we want to test, and that's not good science. The other problem or challenge that we have is that we have a ton of measurements to choose from. So how do we even choose? So here I'm showing you a review or systematic review on kinematic assessments for upper limb movements using technology and non-using technology. And one might conclude that, well, probably we should maybe select the one that most people use. But the measure that most people use might not be actually valid or reliable or sensitive, right? It's not a popular vote approach. So what we're advocating for is to generate constructs of assessment based on our understanding of human movement or motor control. To give you an example, we can create a construct for movement smoothness. So we can say smooth movements are those movements that are composed of a few sub-movements that are closely spaced in time. And unsmooth movements result from the superposition of a large number of sub-movements with loose temporal packing. So this is a subjective interpretation, but that allows us to simulate different movements and test different metrics to evaluate how they might perform in the real world. So for example, you can simulate a movement composed of just one bell-shaped profile, velocity profile, and then you can have movements that have more sub-movements, right? So you can see that you have 2 peaks here in the velocity profile, and these sub-movements become not so close in space in time, and you can look at different measurements and see the response to that, to measuring that motion. You can see that some of the measurements do not have a monotonic response, so you can already rule those out, and a few of them have that monotonic response that you might expect from a measurement that is reliable. So you can tease out which measures are good and which measures are bad. So some of the things that we can do, for example, is you can take the same movement and see whether they are consistent with the underlying measure of construct. So you can evaluate whether the measure that you do, the algorithms that you develop for an IMU, for a wearable sensor, are consistent with the measurements that you develop for a motion capture system when you have different access to different variables. You can, for example, do sensitivity analysis on whether the specific choice of variable affect interpretation of measurement. And this is the recent publication that we have in sharing these results for someone that is interested in looking for that. You can also look into the sensitivity of, for example, gravity when you're measuring that. So think about using a wearable sensor, and you're doing an arm motion. Because of the rotation, the projection of the gravity component might affect the way you interpret the movement itself, right? So we can do sensitivity analysis on that as well. Another challenge that we have is when we want to implement these things in clinical practice is that it needs to be scalable. And we tend to think that, well, we also need data and we need to have better reports. So think about the reports that we can get nowadays from the different commercially available systems. You may get 1 or 2 page PDF report, but if you have 10 patients, 20 patients, and then you're measuring more often, you may end up with a huge number of reports that are not really useful to deliver or to change the intervention itself. So how do we scale this up in order to add value to the clinical practice using this technology? One way is, well, you may measure more often, but not too often. Let's say 3 times per participant, but that's also not good enough. So what we did in the past was we tried to look at the interpretation of measurements based on how often you would measure someone. So what I'm showing you here is one patient that came to our clinic for multiple days. In this case, there are 9 days. And we asked them to walk 10 meters at comfortable speed. And we use a commercially available sensor to measure different part of gait parameters. So what you see here in the spider plots are the different parameters. So the bigger the spider plot, the better the patient performed. So you might think, okay, I'm going to do 3 measurements for this participant: baseline, intermediate assessment, and after therapy. So for this particular scenario, you might conclude, well, the patients start pretty well, right? The measurements are, the spider plot is really full. And after therapy, it actually got worse, right? But what if we have chosen a different day to perform these measurements? So in this scenario, we might have started with a baseline, which is very small, and after therapy, it became better. And we might conclude that the patient is improving a lot. So again, we might end up with a self-fulfilling prophecy if we don't take this into account. So this is not useful to adjust therapy, and it's not useful to evaluate progress over time. So what we need to have is enough data collection so that we can generate models of recovery. So what I'm showing you here, it's an example of how we use these data from these 9 days. And this was just a very simple general linear model. And what you can show to the clinicians is the output of the model, okay? So the output of the model shows how the patient is more or less evolving over the days of therapy. And you can see how this particular participant might be improving in some parameters at the expense of, for example, strike angle here at the bottom right corner. Interestingly, this type of model matches the subjective perception of therapists when they report the improvements of the patient. So the take-home message here is we need to increase the amount of frequency of contextualized recordings to be able to reduce the effects of different sources of variability. So how to achieve that? Well, you need better sensors, and we need sensors where we can have access to data. The problem is access to raw data from consumer-grade sensors is not ideal. One problem is, well, you may not have access to the raw data. I mean, the linear acceleration, angular velocity, magnetometer. You may only have access to, I don't know, consolidated activity counts, for example. And even then, when you are using those sorts of systems, you might not even get the same data twice because the data resides in the servers from the providers of this technology. So there's the need of having that unrestricted access to raw data in order to move the field forward. The other problem is, well, you may have research-grade sensors, but the problem is they're expensive and these are not scalable. So just to give you an example, 15 sensors from this brand may cost you around 50,000 Australian dollars. 50 sensors from this brand may cost you 45,000 Australian dollars. So how can we perform clinical research? Let's say we want to collect data on 100, 200 participants, where we need access to raw data, but with these kind of sensors that are extremely expensive. So at UQ, we have, and the James Strano Institute, we're trying to consolidate people that are working on developing their own solutions for e-health platform and enabling data collection using wearables. So what we want to have is a brand agnostic sensor data collection app with a brand agnostic user input data collection app that allows you to collect data from sensors from your phone, allow you to upload data from from other systems, so motion capture, EMG, etc. Consolidate everything within one server, so we can develop data analytics and algorithms, and you can have a web portal dashboard. So that sounds pretty much like radar-based, right? So essentially, what we want to have is that tool that enables multiple clinical studies. So I'm particularly interested in stroke rehab. Many collaborators are interested in orthopedics, in low back pain, in telehealth, and so on. And such a tool will actually allow to not reinvent the wheel, but rather work collaboratively. So we started collaborating with the Hive and with Radarbase, and we're really happy with the results that we have so far. So besides that, we're also working on open access wearable systems for measuring synchronous movement recording. One problem that you have as well with commercial sensors and even with research-grade sensors is the inability to do well-synchronized recording. So you can imagine that you want to measure posture for the spine because you want to investigate the effects of posture on low back pain. You need to be able to have two sensors that are recording synchronously for a period of days if you want, okay? So we're creating this tool, which hopefully allows us to collect more data collection, and enable more collaborations. And we're trying to do everything with off-the-shelf components to have an open access, do your own instruction manual, and hopefully integration with radar-based as well. So 15 sensors of these may cost you around 2 to 3K, more or less. So we believe that this might be a more scalable solution, at least for research. So stay tuned for some open access publication that is coming up soon on that. So we're pretty excited about the preliminary results from this. So we're doing some preliminary verifications on that. So we're evaluating our own sensor against different commercial sensors. So we are putting those sensors in our robotic platform, and we're having systematic vibrations. And what we can measure, for example, is the synchronicity between those signals. So just to give you an example, actigraph over the span of 15 hours might shift around 2 to 3 seconds. This sensor, without a synchronization mode, might shift around 10 seconds overall over a period of 15 hours. And depending on the settings that you have, may also shift about 3 seconds. So again, you may think that this is not too much time, but think about trying to measure coordination of movements. So if you want to measure the coordination between your arm and your trunk, you need to be able to have well synchronized recordings. Otherwise, the measures that you get are completely erroneous. Some of the best sensors that we have in terms of synchronization, for example, the APDM, show absolutely perfect synchronization. And our own sensor, it results in less than 1 second time shift within 15 hours. So these are promising results. And of course, I think we believe we can improve that as well. Just to leave time for questions as well. So if you would like to get involved, I'm doing an open invitation to please get involved. We're using these tools to develop and validate movement assessment directly from wearable sensor data. So what we do is we create very systematic studies where we use different types of technology, wearable sensor, motion capture, computer vision, to make sure that the measures that we develop are consistent. And we're also using radar-based. So together with the Hive, we're developing this app where what that is allowing us to collect well-segmented, contextualized recordings using different sensors. So in the example here, for example, we may ask someone to go through a series of activities like walking, sleeping, cooking, and so on. And we should be able to partition those recordings on the fly and generate classifiers that are specific to the population in questions. So feel free to reach out, and thanks for listening, and looking forward to collaborate with you.